Excellent. Thank you both for all that you do for this. So it's a pleasure to have Ying Chen with us today. So I appreciate you working through the scheduling issues that we had in the past and rescheduling. And I'm super excited to hear the work that they've been doing in developing this real user's manual is the way that he kind of pitched it there, and the work that they're doing with their Luxendo lattice light sheet. I really enjoyed the source of your inspiration, Yang Chen, so I'm just going to read it real quick. I asked for a short bio, and he says, I get inspirations from submarine novels where the submariners know every part of the ship inside and out, and they can troubleshoot it and fix it because you can't really call tech support when you're under the sea, I suppose. And I think that really applies to a lot of the ways that, people tend to think about microscopy as well, is getting in there, getting your hands dirty, and really being able to fix everything yourself. And so seeing what you do in the rest of your work, it sounds very much in your wheelhouse. So I'm excited to hear your presentation today. Floor is yours.
Thank you very much, Brandon, and everybody for having me here. Okay, let me just do it now. And, well, before I actually go to the user manual, I'm just going to show you the microscope itself. So this is our new toy, still in the box. It could hardly fit into the lift, but we're very lucky it was just right size. So this is it, the Luxendo InV Spin Lattice Pro light sheet. So it has two cameras, and there's an L-shaped structure up there which houses the SLM, spatial light modulator, and then it goes down where they have the optical path that comes up here. The two objectives, you can see it pointing upwards, water dipping. And here's a diagram that's in their user manual for the users. So this, let me get rid of this window. Yeah, special optics, illumination objective, and then that's a sample holder, and Nikon 25 times NA 1.1 detection objective here with the motorized refractive index correction collar, so you can control it from software, and you can see that it's actually not the usual 45 degrees. Yeah, and that's because the two objectives are quite different in diameter. And if you're curious, we could ask Malta how they actually calculated or decided on the exact angles. I can't remember what exactly it is. Yeah, so yeah, he might be able to tell us later. And okay, let me see why my buttons are working. Okay, so the microscope is actually correct, wavefront corrected. So the engineers actually do a Shack-Hartmann wavefront correction. As for the details, Malta could tell us a bit more about that later, if you want to know more. And this is the Gaussian beam in the stationary mode. So when we actually do the light sheet imaging, this beam will scan in the vertical direction, and of course the width of the beam, the waist of the beam can be adjusted. This is the one of the narrowest ones, with a very narrow beam here. And yeah, just to show you a few examples of the different beam patterns that this microscope produces. The bezel beam, as you can easily tell, and you also have the airy beam, the curved one, and then of course you're probably more interested in the lattice patterns. So this is one of them, the high density. We have a few different versions. We have the rectangular ones, we also have the hexagonal ones, and this is a lower density version. And there's also one that has the main beams that are more widely spaced out. So you can see that we have beam patterns of different heights and different densities. Yeah, and also one good thing about this microscope is that you can actually upload your own custom SLM patterns. So what we can do is to use this SSPIM app, which you can find here, to generate the beam patterns, which are the Fourier transform of the actual beam that you see on the sample plane. So I think this is, if I remember correctly, this is the Bessel beam pattern that I tried generating from this app. Yeah, so you can upload anything you want. And okay, and onwards to the sample holders. So this is, remember I showed earlier that between the objectives, there's a sort of a triangular sample dish. So this is one version which is sort of handmade. So you just cut a piece of FEP foil, which has the same very similar refractive index to water. And then you use this black colored mold to push the foil down into this dish with some silicone sealant applied to the edge. Yeah, and then you just leave it for a while and you have the dish. And there's also this single-use dish made by EBD, which also has FEP foil stuck on it, but it's ready-made and it's sterile. And actually, one of our PhD students discovered that after using it once, you can actually pull off the FEP foil and then stick a new piece of FEP foil on it. Although it looks a little untidy, it actually works. So this is not a very good example because you can see that over this side, the foil is a bit crumpled. But if you do it properly, you get a very smooth dish with a depression that you can use. Yeah, so we actually found this slightly easier to make than this one. Yeah, so most of our users are actually reusing this supposedly single-use EBD dish. And so initially we were using the silicone sealant to stick the FEP foil, but one of our zebrafish, which shown here, our zebrafish researchers actually used about, was it 1 or 5% methylcellulose to stick the FEP foil. So as you know, methylcellulose is water soluble, but apparently the foil remains stuck long enough for the imaging. Yeah, so that works too. Yeah, so here's one of our postdoctoral research fellows, Dr. Kathleen Tay. She's actually using a glass pipette to deposit the zebrafish embryo onto one of the dishes. And it's a slightly tricky sample preparation procedure that requires very steady hands. Yeah, because you want to orient the fish in the correct way such that it's in the best direction relative to the orientation of the light sheet illumination objective. Yeah, to get the part of the fish you want. Yeah, so she's doing that. And this is actually another sample holder, not a dish, but actually is a slide for live cells. Yeah, so this is just a normal microscope slide that has been cut to size, and you have the two 3D printed screws that secure the slide in place. And then you just slot this dish into the sample holder. So we are still looking at how well this dish works, because there's a possibility that the cells are not very, very happy when they are suspended upside down. So unlike on a normal confocal microscope where the cells are just growing on top of the glass surface, In this case, the cells are actually hanging upside down. Yeah, so we are not yet sure if that might affect the behavior of the cells or the growth and so on. Yeah, and this is how the sample dish or the sample slide is slotted into the holder, and it's secured by a hex screw, and the chamber is filled with water or PBS or culture medium. And that's just to show you the user interface for the microscope control. So we have the light sheet beam alignment controls here. So you can adjust the position of this light sheet left and right, up and down, and also the rotation in 2 dimensions. Yeah, so we actually find it single direction because some of it has really been aligned by the manufacturer. So we only have four different things to adjust here, and yeah, so it's quite user friendly. And in the middle column are the laser controls and the patterns we want to use, and dichroic mirrors and emission filters here, and the camera exposure settings. And over here, the stage controls. Yeah, so the microscope can also do stage coupling. So in a normal Z stack, the light sheet goes this way. And in the stage coupling, you can actually set the Z and Y values such that instead of moving in this direction, the stage will move like that. Yeah, so oops. So if you have cells spread out over a flat area, you can actually move this way. Yeah, as shown here. So usually you move the stage either this way or that way, one at a time, but you can set it to move horizontally. And after that, if you do the stage coupling, what it does is to give you this, is to reconstruct the stack in this way. So it's not the other way of reconstruction where it actually interpolates and gives you orthogonal stack, a rectangular one. So the slices are still sort of, oops, the slices are, yeah, offset from one another objects in the correct shape. And here is actually just to show you the high-speed imaging of the zebrafish heart. So I think on the left side is the normal wild type, on the right side is a diseased heart. Yeah, so if you do a single plane imaging, it can actually go very, very fast. And the next one is, okay, let me try to get to the next slide. I think I'm sort of stuck here. Okay. Yeah, so I'm just going to show you a 3D animation. So we tried to image a spheroid. So it's the sample is prepared by Celestine and Selwyn from Mechanobiology Institute, and the microscopy was actually done. And of course, my colleague Tong Yen, who was in the meeting, she actually did the video. It's here. Yeah, so this was actually a spheroid that was deconvolved after imaging. So it appears clearer than the raw data. Okay, yeah, so just to quickly show the kind of images that we managed to make with the microscope. And back to the slideshow. And yeah, another thing that this instrument can do is structured illumination. Yeah, so because you have the lattice patterns, and then yeah, you can actually when you just add up all the different lattice positions. Yeah, and then the third one is the sim result. Okay, and of course, one other interesting thing that our facility or our institute, the Center for Bioimaging Sciences, is known for is FCS. Yeah, so some of our labs do FCS, and turns out that this lattice lightsheet microscope can also be used for FCS, but it's not the traditional confocal point FCS. It's the imaging FCS. So instead of collecting a single point, we just collect the FCS for the entire image at once. So we have lots and lots of data. And this instrument can do that because because of the design. It gives us control of the lasers and of the camera's direct control. So we can actually do quite a few more things with this instrument than we can if we had another instrument such as the Lattice Lightsheet. Yeah, so this guy here is Daniel Ek. He just finished his PhD, and he's the one who actually he's the main person who developed this Fiji plugin called IMFCS. So if you search imaging FCS or you go to this this link here, yeah, so that's their lab website with the Fiji plugin to do FCS, and you can just launch the plugin and it already has the drivers to connect to most of the cameras. Yeah, so you can immediately start doing FCS, and yeah, and so what happens is that instead of having the microscope control the cameras and the lasers, we disconnect the cameras and lasers from the microscope control, and then we directly control the lasers using the Omicron software. And we directly control the camera using the FCS plugin. So because of that, there's no shutter delay and so on. We can run the camera at a maximum frame rate to collect the FCS data. And then by having direct control of the lasers, we actually keep the lasers constantly on instead of turning on during the exposure and turning off in the interval between one exposure to the next. Yeah, so this gives us a lot of power to do a lot of interesting things. And as Martin mentioned to me recently, they have recently modified their microscope control software to be able to leave the laser on constantly. So in the future, we could control the lasers directly from the microscope software instead of disconnecting and then having to use Omicron to control it. Yeah, so that would actually sort of save us one step or a few steps in the procedures. And yeah, this just to show a poster that the research fellow I mentioned earlier, Kathleen, she's actually did some work using the imaging FCS on the Lattice Lightsheet microscope, and here's the poster. Yeah, so we have actually found it quite useful. Okay, and I guess I should really get to the user manual, which is actually the main topic of my presentation. Yeah, so this is just to show the example of what I call the takeoff checklist. So, when you are flying a Boeing 747, you always have a takeoff checklist, even if you are a very experienced captain. You always consult the checklist to make sure you don't miss out any steps. Yeah, so this is the same spirit here. So in order to set up the imaging FCS, first you exit the Lux Data Hub, which is a camera control, by doing this, and then you have to flip the switch on one of the cameras to the off position, so that the FCS or the camera control software will connect to this particular camera. Yeah, because it doesn't require the dichroid. So I actually explain the reason for doing things so that the user can understand why it's like that. Yeah, because personally, when someone tells me not to do something but doesn't explain why not or what will happen if I actually do it, then yeah, I actually feel a bit annoyed because yeah, I want to really understand how it works. So I try to take the trouble to explain it. And then turn off the lasers if they're on, and click the start live to keep the shutter open. So after that, how to return the control to microscope. And then, yeah, and this is how to actually use the Omicron to control the lasers. Yeah, you have to do some very specific things. Set it to APC mode and for these wavelengths, and then for 561, which is a DPSS, you have to set it to this particular mode. Yeah, so what happens after that? So you have to turn off the laser because yeah, that's very important, because if you just do this, the laser will be on and then your sample will be continuously blasted by the laser without any protection. And then yeah, what to do to reset the lasers. Yeah, because if you don't do this correctly, then the next user who's doing the normal imaging with the light sheet microscope will have a problem, because then he or she won't be able to control the lasers from the microscope software. Yeah, and then you have to set it back to 100% and so on. Yeah, so the steps are, I just make sure that every single step is laid out clearly, so there's no mistake. And okay, just let me quickly go through the rest of the manual. You can actually download the PDF from this temporary link here, short url.at. I can, wait, okay, hang on. Let me escape. And then I can copy this. And then I can paste it on in the chat. Okay, but I'm not sure how to. I'm not sure how to get to the chat, but it's okay. Maybe you can just, if you're interested, you can just type this link into your web browser. We'll just give it a few more seconds. Yeah, and here's the menu. So it's not like the usual manual for core facility microscope, because it's much more detailed, and it doesn't actually have any screenshots or pictures. Yeah, so we also have the quick start guides, you know, with the screenshots and the basic steps you have to do to get a microscope turned on and to do the basic imaging. Yeah, but my focus in this case was to come up with a complete manual of everything, not just for the users, but also for the facility managers. Yeah, so it serves a dual purpose. And I'll just scroll through quickly. The great thing about this LaTeX is that you can actually just mouse over any section you want and you click on it and you go straight there. Yeah, so that's very convenient. And the manual covers the entire workflow. Yeah, so you know, it's not just about using the microscope and getting the images, but the sample preparation is a very important part of the microscopy. So there's an entire chapter on sample preparation. Especially for this microscope, because the sample holders are not the normal kind. Yeah, so switch on the microscope and the sample preparation. Yeah, so there are detailed instructions on what to do, alternative methods of doing it, and what are the pros and cons of different methods, and things that you have to be careful of. And also there are footnotes on you know, what FEP is, and what are the material safety that you have to pay attention, like do not heat it to high temperatures, and what kind of silicon sealant we are using, and so on. I mean, this kind of information may not be important most of the time to most users, but you know, if you're trying to do something unusual with the microscope, then all this information is here for you to decide you know, whether you can actually push the limits or not. Yeah, so different mounts, and then okay, microscope alignment is, yeah, what I showed in the software interface earlier about the adjusting the position of the beams and so on. So yeah, let me just go quickly through. And then yeah, and of course, one of the highlights of this particular instrument is the variety of beam patterns you have. Yeah, so there are some just some basic descriptions and explanations of the variety of beams you have and what they can be used for. Yeah, so you have, for example, if the static light sheet, it gives a constant light dose that's good for photon quantification, such as in FCS. Yeah, so the user can actually read it and understand yeah, what the microscope can do. And an airy beam is a curved beam that can reduce shadowing and striping in highly scattering or pigmented samples. Yeah, so yeah, if they really want to maximize or optimize what they do with the microscope, they actually have some guidance here. And of course, the lattice patterns and how to set the distances and so on. Okay, custom SLM patterns and okay, image acquisition. So yeah, they're very detailed instructions. And let me just quickly go on to the end of it. Yeah, so time-lapse high-speed video and yeah, direct camera control. That's where I showed the procedures for yeah, for doing the FCS. So, and of course, for direct camera control, you have several options. So you can control it directly using our imaging FCS plugin. You can also control it using the Hamamatsu's own software, which is yeah, I explained it somewhere here. Yeah, because the Hamamatsu software gives you more control over the camera. And then of course there's Micromanager here. Yeah, so it works with Micromanager as well, the cameras. Yeah, Tokupic is the Hamamatsu own camera software. Yeah, and actually, yeah, this was connecting your own camera was something that we were thinking of, but right now we haven't actually done it yet. Yeah, so yeah, that's like under construction. But of course, there are no plans to do it. Yeah, because so far none of our users actually need to do that. Yeah, but yeah, that's actually possible if you really needed to do that. But it's actually very yeah, it will be a tricky process because after you connect your own camera and you want to connect back the supplied cameras, then of course you have to do all the realignment and so on. Yeah, and actually, okay, you have the structure elimination. Yeah, so it also describes in detail how you can find the FFT peaks and all that. Yeah, fluorescence correlation spectroscopy, so one of the special features. So I mean, we are sort of proud of this because you know, not every light sheet microscope can do this or can be configured to do this. Yeah, experimental PSF. How do you get the experimental PSF and what values you have to input into the plugin? Yes, and of course, the last part of the microscopy workflow is the image processing. So as you know, light sheet data are very huge. Yeah, so there are certain challenges associated with processing of light sheet data, and there are different options that we have. So Luxendo has its own image processing software, and of course, yeah, the image viewer, image processor, and there are a lot of settings you can set. So yeah, when the engineers and when Malte himself actually came down to our facility a couple of times to give us training and set up the microscope, they told us a lot of things about you know, like what settings to use and so on. And I sort of tried my best to write down everything they told us because there are so many things that if you don't actually write it down straight away, you just forget it, and then you have trouble recording it later. Yeah, so a lot of this manual was actually done during those training sessions and during the discussions with the engineers, where we wrote everything down. So after that, yeah, we have everything, and we know what to do. And okay, it's coming to the end already. So there's tile stitching and oh yes, and of course deconvolution. Yeah, I learned that deconvolution is quite an important part of light sheet imaging to get the best possible resolution and quality out of the data. Yes, so there's an entire section devoted to that. So we have Huygens, so we use that, and it explains to the user exactly what values you should put into the system, including the fill factor of the objective and so on, and the light sheet direction and basically everything. Okay, and of course Arivis Vision 4D, which came with our purchase. So yeah, we have that's good because apparently it can handle very large data sets, yeah, without using a lot of RAM. And then also yeah, we also give some comments about how MRIS can be used, and yeah, and what is good for and what Arivis is better for, and so on. And Fiji, of course, Fiji is actually quite big at our facility. So because obviously it's very versatile and it's free and open source, so it's highly accessible to users. Yeah, so we make an effort to help them to use Fiji as well. And yeah, of course, there's some advice on what you can do using MATLAB. So I actually tried playing around with this myself. Yeah, so this is from what I found out. And we have high performance computing at our facility as well. Yeah, we are one of the facilities with our own HPC nodes, so they can actually run their stuff on it. Yeah, clean up switching off. And also, unlike most of the time, the user manuals for the facility instrument won't have the literature, but I think it is useful to actually cite the literature that I got information from and actually give the literature here. So, for those users who really, really want to go deep, they can actually refer to the literature. Yeah, okay, great. Yeah, that's it. That's it. And then I just quickly show this particular slide because actually I just wanted to give some insight on the choice that we had. Yeah, so at first when we were looking for a lattice light sheet, we were sort of making a decision between the Zeiss lattice light sheet and Luxendo. So there are several obvious differences. Like for Luxendo, as I mentioned, as I explained, you have much more control, and then you have more flexibility in the beam patterns. Yeah, so you can do a lot more different kinds of things with it. Whereas with the Zeiss instrument, you have a limited choice of beam patterns, but it's actually considerably easier for many users because you can use a normal microscope slide, or you can use a normal petri dish and just put it on the microscope and close the lid, and then that's it. You can do the imaging. I mean, yeah, so you have to align it still, but alignment is actually quite simple. Yeah, so the Zeiss microscope is actually, you could argue that it's more suitable as a facility instrument, because it's more user friendly and it's more of a straightforward. So users can immediately start using it without having to modify their sample preparation protocols. Whereas for the Luxendo, yeah, you have to get used to the sample dish, which, as you saw, can be quite fiddly at times because you have to turn the fish in the right way and all that. Yeah, so in the end, obviously, we chose one over the other. So I wouldn't say it's better or worse or what, but it really depends on what you prefer and what advantages of the instrument that you want in your facility and what other instruments you have. Yeah, actually that's about it. So I just want to thank various people. So Zheng Chao and Wei Jia are the two engineers from Saint Asia distributor in Singapore. Set up and line instruments. Because after from second institute, came down to Singapore to actually do alignment as well and to optimize the setup and everything. And Tong Yen, my colleague, who actually corrected many of my mistakes and gave a lot of advice because she's actually much more experienced in the facility than I am. And of course, some of our researchers, Kathleen, Yu Jing, and Rutupana, Nitin, Shiwen, they did a lot of things for us. They kindly provided samples. They provided ideas of all sorts. Yeah, so we're grateful to them as well. Yeah, actually, I think that's it. Maybe we should Mauter should talk instead because obviously he has much more knowledge and expertise on it. Thank you very much.
So I'd say at this point, we could turn it over to you, Malta, and then we can also open it up, general audience Q&A as well. I think now we're at 10:44. Typically go to 11, so we have about 15 minutes reserved for questions. But yeah.
Maybe just a quick word from my side. Thanks a lot, Yang Chen and Tong for this presentation. It's quite great to see what you're actually doing with the microscope, and we didn't necessarily have this, especially the FCS application, in mind when we designed it. So it's quite impressive what you guys established. Also from what I see, the user manual you put together is actually much better than what we provided you guys. So happy to see that. So I haven't really prepared anything, but I'm happy to take any questions when it comes to technical details and whatnot. Maybe one aspect that I would like to point out is that the complex handover of laser control and camera control to external software is only for this quite specific FCS application. So conventional imaging is fully controlled out of the microscope software, obviously.
I had a question about the FCS. Sorry if I missed it, but could you just say a little bit more about the timing? If you have the pattern and if you have any dithering or anything like that, is it, what sort of considerations do you have to have in mind as far as the speed of imaging versus the dynamics you're trying to measure and the illumination?
So for the FCS, we recommend, and I think that's also what's typically being used, to use a static 2D Gaussian light sheet. So we're not scanning, we don't use any complex patterns because that's the most obvious thing to do. And it's basically, when I started light sheet based FCS, basically what we used, it was a very, very generic design with a cylindrical lens, etc. Here we do not have a cylindrical lens, but an SLM to create a 2D light sheet, but it's the same pattern basically. So you do not have any modulation in space or time of the light sheet during FCS acquisition, because this can be quite detrimental to FCS data. Then in terms of acquisition speed, probably Yang Chen knows better how fast you can actually image. Within our software, we can run, so the system is equipped with Hamamatsu Orca Flash 4.0 cameras. So as CMOS that are good enough for FCS imaging. We can run them with up to 500 frames per second, but I think out of the ImageJ plugin, they can be operated at higher speeds. And then when you're in the range of, let's say, a millisecond or better, or below a millisecond of frame rate, then you can typically sample most biological processes, not necessarily photophysics or fluorophores, but dynamics or diffusion of molecules, even down to GFP is something you can probably sample nicely with such a frame rate. I mean, faster is better, but at the end of the day, you also need photons. So,
right.
Typical FCS problem that you may remember.
Yeah. So is it typically done with a single frame, or can you go in 3D, or I guess that comes back to the cellular dynamics you're looking at?
That's a good question. I mean, I think, correct me if I'm wrong, Yang Chen, but I think in most cases it's used just a 2D. I think 3D would be just another level of complexity of data analysis. I think what the Imaging FCS plugin, this has been developed in Thorsten Roland's lab at NUS in Singapore, is probably the best you can get in terms of imaging FCS. But I think it's still 2D, which from a data processing and data interpretation point of view is probably already challenging enough sometimes.
Yes, yeah. So far, our researchers from Thorsten's lab, they have only done the 2D as far as I know. Yeah, and so we have found that it can actually, the exposure time can actually go down to 0.1 milliseconds. But as Malte said, there are not enough photons. So yeah, what they have been doing so far is just to use an exposure time of 1 millisecond. But of course, to get that, you have to have a very small field of view. I mean, you have to reduce your ROI to, like, I mean, I don't know, 16 pixels by 256 or something like that. Yeah, not the entire frame. Yeah, so it can actually go that fast if you need it to.
Very nice. Thank you.
I think we had a question from Alexander. I don't know if you'd like to ask it, or I can simply ask it here. Question is there a sample holder to fix square or round cover slips upside down?
So what we ship the system with is a square cover slip sample holder. For major reason is that there's not too much space between the objective lenses, so it has to be as narrow as 3 to 5 millimeters in width, so to fit in between the two lenses, because the focal plane is, I mean, you see the sketch at the beginning, right? So basically we have the focal spot is really somewhere in between the lenses, so we have to somehow fit it into the space. We also played around with a version for circular ones with, I think, 3 or 5 millimeter diameter, but this turned out to be quite fiddly, to be honest. So we dropped them quite often. This was not the most practical thing to do. I mean, there probably might be better ways than what we tried first, but in this kind of 1.5 version 1.5 we are working with at this moment, we basically prefer to have this rectangular shape. But so at the end of the day, everything is possible as long as it fits in between the two lenses with a holder. And we are usually quite flexible and supportive to adjust to specific needs, and to have basically a customized design for circular ones, for rectangular ones, etc. I think one point to note is that there's these two modalities of sample mounting. One is this upside down approach for cover glasses, where you can basically grow cells and then have it really upside down mounted. Or the other way is what you saw as well, is these FEP based kind of like trough shaped sample holders, which is more suitable for larger samples like zebrafish. That's maybe also advantage of this approach is that we can actually image also zebrafish. So the size, maximum size of samples you can image on this instrument is certainly in the range of a couple of 100 micrometers, like zebrafish at certain developmental stages. And then, of course, at some point, the creation of complex patterns in complex tissues becomes challenging, and it's not necessarily possible to establish a complex lattice pattern inside a zebrafish when light has to travel through parts of the yolk or something like that. But then we can, of course, fall back to more robust patterns like a Gaussian beam or a Bessel beam. And that's probably the flexibility that this system offers compared to other commercial implementations. So it comes, of course, in a way for the price is a little bit that it's a bit more difficult or more cumbersome to use sometimes, but of course it offers more flexibility. So it's really basically what you need, right? If it's really a routine system that you would like to have, then it might not be the most obvious choice. But if you have a broad range of samples and like to play around and maybe even upload your own beam patterns, then that is something we definitely support.
So we have another question in the chat. Guess I can field it as well. Is there anything on your wish list on the illumination side? More wavelengths, higher power, speckle reduction? Anything else? Or are you pretty much set?
Probably more a question to Yang Chen, I guess.
More wavelengths, higher power, speckle reduction.
I will add one.
Yeah, I mean,
SLM capable of 405 excitation.
yeah, yes, it has 405, but yeah, Malte can probably give more details. But I think, yeah, what I was told is that the SLM isn't optimized for 405.
Right.
Yeah, so you can use it. Yeah, but yeah, it may not be the patterns may not be optimal.
Yeah. Exactly. So it's a bit out of the ray of the spectral range of the system. You can use 405, and your system does have a 405 nanometer laser, right? If I remember correctly, but you will probably have to restrict yourself to more basic patterns like a 1D, 2D Gaussian, or maybe a Bessel beam, but more complex patterns that's difficult to create at 405. So it covers the full spectral visible range, but 405 is really a little bit at the edge. But for basically landmark imaging of nuclei, for example, for that, it's definitely good enough.
Okay, and of course, back to the wish list. Yeah, I mean, personally, of course, I mean, the way I do microscopy is that I would always want my microscope to be able to do everything I can imagine, because, you know, obviously, our users right now, they are quite happy with the Lattice Lightsheet, that it has the wavelengths they need and it gives them the images they want. Yeah, but you know, there's always a chance that some user would come to us one day with a very, very unusual request. They need a special wavelength, or they have a very, very difficult sample where it's very turbid or very thick, and they just can't get a good enough image. Yeah, so you know, that's when I will wish that we had yeah, stuff like higher powers, speckle reduction, adaptive optics, for example, which was actually one thing that we were discussing with Malte. You know, whether it's actually possible to have adaptive optics incorporated into this microscope and so on. Yeah, and then I've got users who needed unusual wavelengths, which are actually quite commonplace in physics. For example, 532, which none of our microscopes actually has. 532, and one of them needed like 325 or something, like UV, for example. So yeah, so yeah, it depends on what perspective you take. So for normal facility use right now, I think we are quite okay with it. I mean, we are satisfied with the features. Yeah, but if you ask me, obviously I always want more. I always want the microscope to be as powerful as possible to be able to do everything.
Hi, Malta. 第一同业.
Hi.
Hello. Yeah. Can you hear me?
Yes, of course.
Yeah. I have one question about when it will be available for the two-channel simultaneous scan.
Sorry, could you say it again?
So when it will be available for two-channel or two-color simultaneous scan using the two cameras at the same time.
At the same time. We're still working on it. So I can't give you a very concrete timeline at this moment, but it's something we're looking into because this requires some reprogramming of the optics. So not necessarily a physical intervention, but we have to work on the software to control the optical elements.
Do you have a grayscale SLM then, or?
Yeah.
Is it okay? Oh, obviously you're doing your corrections, so yes, it is. Okay, well, if there are no other questions, I think we're pretty much at time. So I think if we can thank our speakers once again for a great session today. I really enjoyed it.
Thank you very much.
Thank you very much. Thank you very much from our side as well.
Yeah, so we'll take a little break for the summer and meet again on September 10th. So